This is the solutions lessons for the part 2 of the notes. This is going to be a review from the beginning of the year. There are 2 types of matter. The first type is the type of matter that cannot be separated by physical means, and that is going to be pure substances. And then within the pure substances, there are 2 types. There's the type that can be decomposed by chemical means, such as compounds. So in other words, if I had water, which is H2O, and I ran an electric current through it, I could break it down into back down into oxygen and hydrogen. And then, of course, elements are the simplest form, and they cannot be broken down any further, even by a chemical change. The next type is mixtures. And if you recall from the beginning of the year, mixtures can be separated by physical means. Things like distillation, separation, boiling point, those can be separated by physical means. There are 2 types. There's the first type, which is uniform in composition, meaning it's the same throughout, and those are homogeneous. And we also call those solutions, which is the title of our unit that we're on. The heterogeneous mixture, of course, has 2 phases, and you can visibly distinguish between its characteristics. So it does not have a uniform composition, and those are suspensions. Those are suspensions. Sorry, my thing just played out on me. And colloids. Lost some of our notes there on that one. And down at the bottom, you can kind of see a particulate drawing. The homogeneous mixture looks uniform throughout. It's the same throughout. And if you look at the heterogeneous mixture, the particles are different. They're not mixed together in a uniform fashion. When we're talking about solutions, of course, that's any substance, solid, liquid, or gas that is evenly dispersed throughout another. It is not the same as a chemical reaction, so we need to keep that in mind. When we're making solutions, it is a physical change because we're dissolving something. Examples of solutions would be saline solution, which you use for contacts. Another example of a solution could be stainless steel, which would be a solid solution. Oops, stainless. Oops, that's supposed to be steel. Thinking and talking at the same time, it's not working. There are 2 components of a solution. The first one is the solute, which is the substance that's being dissolved, and you'll see in your notes that it's the substance that's in the lesser amount, and the solvent is what is doing the dissolving, and it'll be present in a greater amount. And from the water video, remember that water is the universal solvent. It is very hard to actually keep distilled water pure and fresh because it's such a good solvent that it likes to dissolve pretty much a lot of the things that it comes in contact with or mixed with. When we are talking about suspensions, suspensions, of course, have very large particles that settle out if it's not continually stirred or agitated. And here's 2 examples here that you can write in. Muddy water and Italian salad dressing would be examples of suspensions. The next type of heterogeneous mixture that we're going to talk about a little bit more extensively is colloids. And colloids have particles that are intermediate in size. They're kind of like between the size of a solution and the suspension, but they do not settle out. Okay, so example of that would be fog, or mayonnaise also is an example of a colloid. They do scatter light in the Tyndall Effect, which we'll talk about here in a second. Colloids have 2 phases. They are made up of the dispersed phase, which is the colloid-sized particles, and then the second one is, this is actually supposed to be dispersing medium, and it's basically what the particles are dispersed in, dispersing medium, not phase. So make that change in your notes, which is basically like the solvent component. Colloids exhibit something called Brownian motion that you can actually see when you look out under a microscope. Here is just some fun facts about colloids and give you some different examples. So blood, paint, Jello, jelly, whipped cream, those are all some examples of colloids. We talked a while ago about the Tyndall Effect, and what the Tyndall Effect can be used for is if you have a solution and a colloid and they both look like clear, and you're not sure is this a solution or a colloid, you can always take a light and pass it through it. If it scatters the light where you can actually see the visible beam, then it is a colloid. If it passes straight through, like we cannot see the beam going through here, then it would be a solution. A very good example of the Tyndall Effect is fog. When we see fog on a headlights, remember when you have headlights, if you put them on high, it's really hard to see because that light particles are being scattered back towards you. The solution process is going to be talking about how we mix things. And so this is called solvation, and that is the process by which a solute dissolves in a solvent. The first one is if it actually do mix, so that means the solute will dissolve in the solvent, and that's called miscible. So if I say something is miscible, it basically means that they will mix and form a solution. If they do not, then we say it is immiscible. For instance, oil and water are immiscible. They will not mix. And then this is just a reminder that when we say something is an aqueous solution, that means that it has been dissolved or the solvent is water. So an example of that, again, would be saline solution, salt water, that kind of thing. This is going to be your left side activity. You're going to write this on page 148 in your notebook. And what I need you to do is, basically this is so that you can realize that there are all kinds of solutions out there. We tend to think of it as dissolving a solid in a liquid, but there are, as you can see, several different types. For instance, a solid and a solid, that's things like 14 karat gold or steel. We call a lot of those metal mixtures, remember, we call them alloys. And then there's some other examples there that you need to make sure you write down. The main thing, though, is you need to understand that you can have all kinds of, right here, different kinds of solutions mixed together. The solution process, continuing on talking about that, we want to talk about first how ionic molecules and water interact and dissolve. The first thing we need to remember or understand is that whenever ions dissolve in water, they do something called dissociate, or what they mean is ions separate. Sometimes we call that ionize. And the water is then attracted to the positive and negative ions, and then basically they surround them. So in the next slide is a visual. So if you look at that, we have our sodium chloride here being dissolved in water, and what we mean by dissociate is these sodium and chlorine particles break apart, and they're individually going around the solution by themselves. Now, this is the chlorine, and this is the sodium. So what happens is, and of course you know water, this is the hydrogen, so these ends are slightly positive, this end is slightly negative. So what happens for the chlorine is it orients itself so that the slightly positive side of water right here is attracted to the chlorine. And then this, for the sodium, the slightly negative side of the hydrogen, of the oxygen right there is attracted. I'm just drawing that wrong. Sorry about that. Let me erase that. Okay. So the slightly negative side is attracted to the sodium, and the slightly positive side of water is attracted to the chlorine. So they surround them. It's called being hydrated. All right. And then if we're talking about when a polar molecule is being dissolved in water, dissociation does not occur. That doesn't mean they don't dissolve. Dissociation is different than dissolving. So absolutely a polar molecule will dissolve in polar water. And when it does, we call this molecular solvation. But if you look right here, this is sugar. And of course, sugar is oriented in different ways. But the water orients itself so that it's attracted to it, because the polar side, the slightly negative side of the molecule, is going to be attracted to the slightly positive side of the water, and the slightly positive side of the molecule will be attracted to the slightly negative. And then the last one is when I try to dissolve and nonpolar covalent within water, and what happens is nothing. A solution does not occur because they are immiscible, and this is an example of oil and water. And water is polar and oil is nonpolar, so what happens is that you get these layers right here because they will not dissolve. Now, you could shake it up for a little bit and they'll seem to mix in, but as soon as you let it sit for any length of time, they automatically separate into their individual layers. Solubility is something that we're going to be talking quite a bit about. We have a worksheet on it. Basically, it's the maximum amount of a substance that will dissolve at a specific temperature. And usually when we're talking about solubility, we're talking about per 100 grams of the solvent. When we are talking about our solutions, the solution is going to be one of three things. If it has not enough solute, meaning I could dissolve some more if I wanted to, we call that unsaturated, meaning I could still add some. It has room for more. If it has the right amount, just enough, we call that saturated. And then sometimes a solution can have more than it should at that temperature, too much of it, and we call that supersaturated. And that is most of the time done by heating the sample up and then cooling it down. So now it has more than if we had tried to just add that same amount at that given temperature. By heating it up, we could dissolve more, and then we cooled it back down, so it's supersaturated. So let's look at a solubility curve. This is our solubility curve. Each line represents a different substance, and so let's look at this line right here. We'll kind of trace it. That's sodium nitrate, so we'll do some examples based on that. First of all, when I'm looking at the line, and if I gave a value and that appeared directly on the line, then that solution would be considered saturated because it has the maximum amount. If I asked you about a value that fell underneath the line, for instance at 40 degrees, if I asked you about 90 right here, that would be unsaturated because I could add more solution, more solvent until I got, no, more solute, excuse me, until I got to this line. If I asked you the same thing at 40 degrees and I said it was 130 up here, that would be supersaturated, okay? So on the line, saturated, below it, unsaturated, above it, supersaturated. Factors affecting the rate, and when I'm talking about this, we're talking about rate. That means how fast, not how much. So how quickly could I get something dissolved? The first thing is agitation. So if I was saying going to make some sweet tea and I threw some sugar in there to make my sweet tea, I wouldn't just let it sit there because it would take forever for it to dissolve. So we know kind of counterintuitively that we need to stir it. So stirring is one of them, and that is because when you're doing that, you're constantly having fresh interactions between the solute instead of the solvent. The next one is surface area. So the smaller the surface area, the faster it will dissolve. So I wouldn't want to put, if I wanted to dissolve very quickly, I wouldn't be using sugar cubes. I would use granulated sugar like we're used to using. And then the last one is temperature. Now, temperature we got to be a little bit careful with because when we're talking about this, we are talking about how fast something will dissolve. It may or may not increase the amount, okay? May or may not increase the amount that's going to be dissolved, but it definitely will dissolve quicker at a higher temperature. And the way that we can remember this is heat it, crush it, stir it. Those are the things you want to do to increase the rate. If you do those things, by heat it, crush it, or stir it, it will dissolve faster. Now, factors affecting solubility, or basically how much, that's a little bit different, okay? That's when we would refer back to that solubility curve. The first one is increasing the temperature. And when I increase the temperature, the solubility of a solid in a solute generally, notice this generally, increases. Most of the time it does mean I can dissolve more. But there are some things that actually get less soluble as you heat them. And interestingly enough, if you look right here at sodium chloride, it is all, I mean, it increases a tiny bit with temperature, but it is not changing very much with temperature, okay? And this is an example you can read and look at there. You've got at 20 degrees Celsius, 87 grams of sodium nitrate will dissolve, but at 80, it's actually 143 grams. Decreasing temperature will also affect, but it will actually affect gases. So if I have a decreasing temperature, in other words, a lower temperature, the solubility of gases in a liquid will increase. So this is an example we like to use is the Coke. If you have soda, Sprite, any kind of Coke, and it is warm, it actually will not have as much CO2 dissolved in it as when it's cold. So it's a good idea to store your Cokes and Sprites and Dr. Peppers in the refrigerator because it will keep its fizz longer as it's colder. The last factor affecting solubility is pressure. And pressure only affects gases in liquids. It's the only thing it affects. And as you increase the pressure, if you increase the pressure, you will increase the solubility of the gas. And there's a law known as Henry's law that says at a given temperature, the solubility is directly proportional to the pressure of the gas above the liquid. So when we're talking about pressure, we're talking about putting pressure on top of the liquid. And here's a little visual right here. As I increase this piston and it goes down, more of the gas particles that are above it go actually into the liquid solution. This is kind of just simple. Concentrated solution, oops, sorry about that, let me go back. A concentrated solution is one in which there is a relatively large amount of solute to solvent for the same amount of solvent, and then dilute is relatively small amounts. So, for instance, you can buy concentrated laundry detergent, and it's got a lot more of the active ingredients in the same amount of water than just regular laundry detergent. And then sometimes we take, in the lab especially, we'll take a concentrated acid and we'll dilute it with water, which means there's less particles from the acid in the dilute solution. And we're almost done with this lesson. First of all, let's talk about, before we're finished, electrolytes. If you recall back from the beginning of the year, electrolytes are a solution that will conduct an electric current when it's in its aqueous state or in the molten state, which means melted. Okay, a very good example of electrolyte is Gatorade and salt water. Strong electrolytes are something that almost completely ionizes, and we need to be, all aqueous solutions of ionic compounds are strong. The strong acids, which you're going to need to memorize those, these are the strong acids right here, and then strong bases, which are hydroxides of group 1 and 2. There are things called weak electrolytes, which only slightly ionize or dissociate, and they will conduct a weak electric current, and they're the weak acids. Acetic acid is a very good example of that, and acetic acid is what is in vinegar. It's just been diluted with water, and we call it vinegar. And then, of course, we have the non-electrolytes. And they're compounds that will form solutions, but because they're not ionic, they don't dissociate, and so they don't have any ions to conduct, but they still will dissolve. And a good example of that is sugar water. If I dissolve sugar in water, which we all know sugar will dissolve, but it will not actually conduct electric current if I was dissolving pure sugar in pure distilled water. And then this is the last slide, and this is just kind of a visual to see things with a high conductivity, which have a lot of ions. They're going to really light that light bulb up. If it's just a small, and we talked about acetic acid, it does it very weakly. And of course, if it's a non-electrolyte, it doesn't do anything. All right, this is the end of the lesson.